Hi everyone, welcome back to the Coding Game channel. In April, I traveled to Italy for the European qualifier for the Programming World Championship. This year, there were 97 teams fighting for a spot in the World Finals, and I was there as a coach of 9 students. In this challenge, the top students from many universities have 5 hours to solve 12 problems. The problems look exactly like puzzles you would get on Coding Game. There's a statement, there's test cases that are provided as well, and you have to submit the source code to be evaluated on the server against secret test cases. If your code solves correctly the problem on all of the hidden test cases, well, you get 1 point on the leaderboard. I managed to solve 6 of the 12 problems, and trust me, the other 6 are way beyond my level. In this video, we're gonna see 3 of those problems, and I'm gonna show you the solutions to those. And in a future video, I'll show you 3 more. The first problem I want to show you is the easiest problem from this year. It's problem A. Well, problems are not always given in ascending order of difficulty, but this year problem A was actually the easiest. What it tells us, well, there's always a bit of backstory. So here we have to organize SWERC. SWERC is actually the name of the competition. It means Southwestern European Regional Championship. You can see here it's written on the top right. Let's read the statement. So it tells us the story of Gianni, which is an organizer of the contest, who would like to select problems for the contest. So we will have n problems, and each of those will have a beauty rating here and a difficulty score as well. The beauty and the difficulty will be integers between 1 and 10. What we have to do is select 1 problem for each difficulty level between 1 and 10 and keep only the one with the highest beauty in each difficulty score. If there's at least 1 difficulty level between 1 and 10 where we don't have any problems of that level, well, we have to print more problems, and otherwise we will print the total beauty of the problems that we have chosen. For each test case, we will have the number of problems that we can use in our problem set, then a description of those n problems. So here we have 2 numbers, bi and di, which are integers between 1 and 10. Then on the second page, we will have samples, and sometimes we will have explanations as well. So here the file is organized in 2 test cases. Here's the first one. So we have 3 problems. The first one has beauty 8 and difficulty 4. The second one has beauty 9 and difficulty 3. And the last one has beauty 6 and difficulty 7. This is not enough to create a full problem set with all difficulties between 1 and 10. So we will print the string more problems. And for the second test case, now we have 12 problems. So now we can use those to craft a problem set of all difficulties, and we are gonna try to maximize their beauty. Here the maximum beauty we can have is 93. So as you can see on the difficulties from 1 to 9, we have only a single problem of that difficulty, and they all have a beauty rating of 10. For difficulty 10 now we have 3 problems available. The first one has beauty 3, the second one as well, and the third one has difficulty 1. So in that case we will want to keep a problem with beauty 3 for difficulty 10. In total, we will have 9 problems with beauty 10 and a single problem with beauty 3. So that's 93, which is the score that we're gonna print here. Okay, let's get coding. So I'll be using the CoderPad sandbox. It's a very practical tool. So you just have to tap pad.new in your browser. Pad.new will open a new sandbox, and you can run your code in any language without having to install anything. Like any programming exercises, we will have the first part dedicated to parsing, so reading the input data. Then we'll solve the problem with a simple algorithm in that case. And the third part will be printing the answer. To parse the input, we will follow the specification. So here it says that we have t test cases. So first we have to read that number, and we'll loop over n test cases. Then here we will process a single test case. So we will do the parsing, solving and writing for 1 test case. In the statement, it tells us that the first line of each test case is n, the number of problems. So I'm just gonna read that, and then we can do a loop n times to read each problem, the beauty and difficulty rating. So here's my loop, and then I want to read the beauty and the difficulty, which are provided in that order, and I will do a map. Here over the input that's split into two parts. So each line will split into two, map the int function to it, and we'll unpack that into those two variables. Okay, so that's the parsing done. Well, now how do we solve that? What I want to do is create an array which I'll call max beauty, which will contain the maximum beauty that I can find for each level of difficulty. I'll initialize all those 10 variables to -1. I have to not forget the -1 because the list index in Python is between 0 and 9 in that list, but difficulty will be given between 1 and 10. Then I'll say this becomes the max of its current value and the beauty value. So now, well, if the current beauty is already higher than the new, I'll keep that. And otherwise, I'll keep the new beauty value that I've just read. At the end of this loop, I will have the maximum beauty that I can find for each level of difficulty. I have to do one check, which is in case I don't have any problems for one or more difficulty levels. This will be very simple to check. I just have to check whether or not there's a -1 in the list. So here I'll just print more problems, which is what was specified in the statement. And otherwise, I'll just print the sum of the max beauty list. Okay, let's run this code now. So I can just copy from the PDF. The code has correctly printed more problems after the first test case and 93 after the second one. So in that case, we could submit the solution to the platform and have it evaluated against all the hidden test cases. That's problem A done. Let's see the second one. The second easiest problem in the order of difficulty this year was problem F, called bottle arrangement. It looks very complex, but there's actually a very clever solution that makes it super easy. The statement tells us that we have to organize a line of bottles with red and white wine. We have critics that will want to taste red and white wine as well, and they only want to taste from a contiguous interval. So all the bottles they taste will need to be next to each other in the line we created. Our goal is to create that line given the constraints of each critic, which will each have a number of white and red bottles that they will want to taste. Let's take the first example. So we have 5 bottles to put on the table, and we also have 3 critics. Critic 1 will want 1 bottle of red wine and 0 bottles of white. Critic number 2 wants to taste 3 bottles of red and 2 bottles of white. And the last critic wants to taste 2 bottles of each. The solution that's provided in the test case is red, white, red, red, white, and let's see why. That solution is valid because the first critic can just take, for example, this bottle and it's fine. They are satisfied. The second critic can take the whole sequence and they will have 3 bottles of red and 2 bottles of white. And for the last critic who needs 2 bottles of each, we can just take this segment and you can see there's 2 bottles of each. There are many possible solutions for this test case, but this is one of them. Red, white, red, red, white. One possible solution involves something much more clever, which is counting the maximum number of bottles of red that any judge will need and the maximum of all white bottles. So the maximum of the red column is 3 and the maximum of the white column is 2. So we can just keep them here and then we can simply generate the row of bottles by taking those 3 red bottles that we need, and then we can put the 2 bottles of white that we need at the end. This will always give us a valid solution because the judges can start at this delimitation and pick however many bottles of white they need in that direction and the number of bottles of red in that direction. The segment will always be contiguous. So for example, here with the 2 and 2, we can take this segment. So 2 bottles to the right, 2 bottles to the left. And so as long as the sum of those 2 values is not more than the number of bottles that we have to put on the table, we will always have the way to generate a solution. Here we again have multiple test cases, so we can keep the same loop as before. Then the first line of each test case will give us the number of bottles that we need to put in the line and the number of critics. So those are 2 variables, n and m. So I'll read those 2 integers. Then I loop over m. So for I in range of m for each critic, so for each of the m lines, we will read 2 integers R and W. Next, I'll declare two variables, so max red and max white, for example. I'll initialize them both to 0, and then I'll define max red exactly like we did in problem A as the max of itself and the red value. This will ensure over the loop that we only keep the maximum value over all R's, and we'll do the same with the white. Then we will have three main cases. The first case is if we have max red and max white greater than the number of bottles that we can put on the table. In that case, it's not possible to solve the problem, because in that case, it doesn't matter which order we put the bottles in, we will need more slots than that. So we'll just print impossible here as specified in the statement. Otherwise, we can just print, for example, red times max red followed by W multiplied by the number of white. There's also a third case we need to consider. It appears when max red and max white, so the number of total bottles that we need, is lower than the number of bottles we are allowed. So now we have too many spaces. In that case, it doesn't really matter which bottles we put in the free slots we have at the end. But we still have to fill them, because otherwise the answer will be invalid. We will provide a line with a lower number that were asked in N. So what we can do here, for example, is redefine max white as N minus max red. This can only increase the value of max white when it's needed. It cannot decrease that, because otherwise we will be in that case. So now you can see that max red plus max white, if you replace those variables, it will be equal to N. So we have three example test cases. The first one, we have 5 bottles and 3 judges, which is the one that I've drawn. So first judge has 1 and 0, then 3 and 2, then 2 and 2. You can see this gives me the exact same solution as I've drawn before, which is 3 reds, then 2 whites. The second test case, we will have 4 bottles and 3 judges. First judge has 2 red and 1 white. Second one will have 1 and 1. And the last one we'll want to taste no red wines and 3 white wines. Here you can see max red will be 2, max white will be 3, but we only have 4 bottles. This will be an issue because now we have to display 5 bottles in total and we only have space for 4 of them. So now I hope my code will print impossible. Yes, perfect. And for the last test case, we will have 3 bottles, 2 judges. First judge will want to taste only 2 bottles of white, and the second judge will want to taste 3 bottles of white. This should give me 3 bottles of white. Yes. So this code appears to be valid as well in the real contests. I would be confident enough to submit it to the judge and see whether or not it would score a point. Well, I've done almost that exact code in the competition and it passed, so I'm pretty confident this code is valid as well. The third problem I want to show you is problem E, called evolution of withers. I find this problem very interesting and I think it involves more logic than actual programming. In this one, we are given 2 sequences of DNA and we have to determine whether or not we can evolve the first string into the second one through mutations. This is a very special kind of DNA because there's only letters A, B, and C. And the mutations we can do is only remove strings AA, BB, CC, ABAB, or BCBC. So if any of those strings appear in a DNA sequence, we can remove them and we can also add them anywhere in the string we want. Okay, so let's say we want to know whether there's a way to turn ABACA into BCBBA. And I'll also write down the strings that can be part of a mutation. In this problem, we only want to determine whether or not there's a possibility to turn one string into the other. And we don't really care about how many steps it takes. And actually, we don't even have to provide the steps. The only answer that's needed is either yes or no. The answer is actually yes. And here is a possible series of steps you can do to turn this string into the other. First, we're going to insert ABAB between the first A and the first B. So that's the first mutation. Then we can delete those 2 A's with this rule and those 2 B's with this rule. Now with those 2 deletions, we will have BAACA. We can do one more with the double A with the first rule, and this will give us BCA. The last step we can do is insert here BB with the second mutation that's possible here, and this will give us BCBBA, which is exactly the same as this string. There are three things that you can notice that will make solving the problem much easier. The first one is that operations are completely symmetrical, which means that every operation can be reversed. That's very simple because we can insert and delete all those 5 strings that are provided. So the opposite of inserting is deleting that same substring, and the opposite of deleting a substring is inserting it again. The second thing that you can notice is that a letter B can pretty much move freely inside the string. Let me demonstrate. Let's assume that in a string we have an AB surrounded by maybe other stuff. It doesn't really matter. In that case, we can insert AB here, keep the A and the B that were original in the string. Then we can simply remove those two groups of A and B, and we will be left with BA. So as you can see, we have inverted the positions of A and B, and since all operations are symmetrical, we can also invert in the other direction. So a B can move through an A in the string, and we can do the exact same with a C, following the same logic but inserting BC instead. So with that property, we can pretty much get the B letters out of the way, and then we'll face a problem that's a bit simpler, which involves only letters A and C. We cannot swap letters A and C, unfortunately, because here you can see in the strings we can substitute. There isn't AC, for example, which would allow us to do the swap that we did with B. So now we can consider that, well, we have a group of B here, but we don't really care about it. Then we have to think about the A's and C's that we have. So for example, we will have this problem because all the B's have been moved to the left for now. And the third helpful thing that you can notice is that any group of even size can be deleted. So for example, here the group of AA, well, obviously can be deleted with this transformation, but also this group with 4 C's, this group can be removed by deleting CC, then CC once again. Any group of odd size can be reduced to only a single letter. So here a group of 3 C's can be reduced to 1 C. If we had 7 C's, we could as well reduce it to 5, then 3, then 1. So any group of odd size can be reduced to a single character of that group. Now this allows us to transform a string into something we could call a canonical form, which means that it's a simple universal way to represent any string. And we will define the canonical form in such a way that if two strings have the same reduction, then we can go from one to another, and if not, we cannot. So for this, it's very simple. We will take all the B's, put them to the left as I did, and then if that group of B has even size, we just remove that. Otherwise, we keep only a single B. Then all groups of even size will be deleted, and all groups of odd size will only have one single character kept. So here, this whole group would become just CA. Now let's go back to my first example. So A, B, A, C, A. We wanted to know whether or not we could convert that to B, C, B, B, A. And the way to do that will be to transform both into the same form that I've defined previously. So we will take first all the B's, then put them to the left. So here we have B and then A, C, A. This operation is actually reversible because, as you remember, B can move freely. Then what I want to do is remove all groups of even size. So here we only have this double A, and so it's gonna have the form BCA at the end. The second string, we will put the B's to the left as well. So B, 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 then CA. And then I will want to reduce all the groups of odd size to 1 and all the groups of even size to 0. And here, the triple B, we can remove those two, and this will give us BCA. Since all those operations are reversible, this gives us a way to go from one string to the other. And if that canonical representation was different between those two strings, well, there would be no way to go from one to the other due to the way we built that representation. The test cases, again, they are given in a loop, and each test case will have 2 lines here, which are S1 and S2, the 2 strings. As I was saying, we will print yes, if and only if the canonical representation of S1 is equal to the one of S2, and otherwise we'll just print no. Here I'll define the canonical function, which takes a string as an input. First, we will move the B letters to the left and reduce them to only 0 or 1 characters. So, well, I'll just say B if there's an odd number of B's in the string, otherwise it will be an empty string. Then to that res variable, we will add the series of A's and C's. So here we will add to the end of res, we will replace all occurrences of B in the string with the empty string, so we will remove all of them. Then, while there's a pair of A in the canonical representation or there's a pair of C's, I'll replace them and I'll just remove the occurrences. And this will guarantee that I don't have any more pairs of A's or C's in my representation. There will be no pair of B's, but that will be handled by the first line. And then we can simply return the results. Now let's try this on the single test case that I've shown you. So ABACA and BCBBA. As you can see, it tells me yes. Let's try another test case right here. So for example, ABC and CBA. The canonical representation of the first string will be BAC and the second one will be BCA, and since we cannot swap C and A, we will not have a way to go from one to another, so it should give us no. Perfect. So that's problem E done as well. Once again, I really enjoyed playing the European Championships of Programming this year. With the channel analytics, I know that around 95% of you who are watching the videos are not subscribed, so well, if you are, thank you, and if you aren't, please consider subscribing to see more content like this. I'll be releasing a video with 3 more problems like this shortly, so make sure you don't miss it if you have enjoyed this one.